everyone and good afternoon. Thank you for giving me the time to present about my own research. The title is about the performance comparison of live CNN models for joint collision avoidance datasets. So, Rifqi here. So let's get on to chapter number 2. Okay, in the slide number 2, it's the content of this presentation. The first is the motivation at the slide number 3, the previous work at the slide number 4, the problem statement in slide number 5, the proposed solution at the slide number 6, methodology at the slide number 7, and the result is slide number 8, and the conclusion is the slide number 9. And then the motivation that why I'm choosing this research is because the uses of the drone is increased significantly in this decade. We know that the drone can see in the field resource, in the industrial application, in the drone agriculture, and the drone inspection as well. And then one of the type of the drone is the autonomous drone. We know that the autonomous drone is we do not need to controlling with the pilot, and the advantages of the autonomous drone is the efficient, low cost, and safe. And then for the navigation of the autonomous drone, we need the system. It's called the collision avoidance dataset. The CSS system, this system have the 3 parts. The one is the obstacle sensing, which is the sensor, the how to obtain the information around the drone. And then the second is the collision prediction, how to predict the incoming collision. And the third is the collision avoidance. But in this paper, I focus on collision prediction. We know that in all of the drone have the built-in camera itself. And then what is how to predict the incoming collision? We use the vision prediction and using the CNN algorithm as the algorithm that predict the incoming collision. But the challenging of the CNN algorithm is need more training data set. That's why in the previous work, the W. Pedro and the 2019 proposed the data set. It's called the collision data set. They compose of the 100 drone collision data set videos. And then they also proposed a CNN algorithm with the VGG16 based, and the algorithm can achieve 94.55%, but the disadvantage of this architecture, VGG16, has a large number of parameters, which means require a big computation. But meanwhile, in pocket drone have limitation processing, so this architecture is not suitable for this drone. And then in the next research, W. Pedro proposed an algorithm, namely neural network pipeline, which is the combining of the CNN, LNN, and FNN. And then for CNN, they use mobile net version 2 as a backbone. It's a lightweight pretend model. But all of the NLP only implement in the big drone. But how to NLP can convert to in the pocket drone? So this is my problems. So the problem is how do we know the NLP algorithm can use in the implement in the limitation computation like a pocket drone. So we try to customize the CNN. We try to customize the blue block, which is the CNN extraction, feature extraction, to change the pretend model and then find which model that have the light computation and high accuracy. And then before we define what is the lightweight pretend model that's suitable for the hardware, we have to know about what is the hardware that we want to deploy in the model. So in this in this research, I consider to use Raspberry Pi 3D Plus, which is the have the 1 gigabyte RAM and only a 1.4 gigahertz clock speed every core. And then according to journal from Ramet Hamidi, Raspberry can run a pretend model with the 45 million parameter with TensorFlow framework. Therefore, we consider to choose only less than 10 million parameter in Keras library and release up to 2022 as the pretend model. So in the right side is the table that the model that I use in this paper. And then for the methodology, we use quality dataset as the material. We split up the quality dataset into the training and the testing, and then using the transfer learning methodology to copying the pretend model that have already trained by ImageNet, and then the hardware what I am doing. One hardware that I am using is a NVIDIA GeForce GTX T1, and then for the hyperparameter we use the input 224, and then we using the augmentation to enlarge the dataset and using the bed size until 16, and the epoch is 100, which is the 50 for frozen weight, and the 50 is unfrozen weight. And then we're using the optimization using again optimization with 0.001 for the learning rate. And then this is the list of the lightweight pretend model, and then we validate the performance using the confusion matrix and LOC curve. And then the result is we saw that in this table the DenseNet have a highest performance, but they have a big computation, which is the 808.690 parameter and need to 28.1 for 8 megabyte access memory. And then the mobile net, this is the choose one. I using mobile net because they have a good performance, but have relative computation. And then this is the result of the